Welcome, everyone. My name is Charlie Bender, and we're here with the AIST Decarbonization 101 webinar, exploring the life cycle sources and measuring of CO2 emissions technology training. AIST webinar guidelines include that each attendee audio has been disabled and questions to the presenter should be submitted via the Q&A feature at the bottom of your screen. The host and moderator will determine which questions are presented to the presenter, and this session is being recorded and will be available for on-demand replay on AIST's Resource Center. Photos or recording of this presentation is prohibited, and if you have technical difficulties, please email them to training@aist.org. The Antitrust and Anti-Harassment Guidelines apply to this AIST presentation. For antitrust guidelines, please do not discuss with others or your own or your competitors' prices, pricing, procedures, or anything that might affect prices, such as costs, discounts, terms of sale, or profit margins, nor anticipated wage rates. Do not make statements about your own prices or those of competitors. Do not talk about what individual companies plan to do in particular markets or with particular customers. Do not disclose to others any competitively sensitive information. Do not propose or agree to any action intended to disadvantage or injure another company. And finally, do not stay at a meeting or activity where any such anti-competitive talk occurs. The AIST anti-harassment policy is strong in that we are dedicated to providing harassment-free events for everyone, regardless of age, race, religion, disability, gender, gender identity, or sexual orientation. We do not tolerate harassment in any form of anyone attending an AIST event. Harassing behaviors include offensive verbal comments related to age, race, religion, disability, gender, gender identity, or sexual orientation, the use of displayed sexual images, activities or commentary in public spaces, deliberate intimidation, stalking or following, harassing photography or recording, sustained disruption of events, or inappropriate physical contact. Participants asked to stop any harassing behavior are expected to comply immediately. Participants violating this policy may be sanctioned or expelled from the event or the membership at discretion of the AIST leadership. I'd like to introduce our moderators. We have David Marshall from Performance Improvement. David started his studies in electrical engineering at Teesside University in the UK and has completed an MBA at Ivey in Western London, Ontario. He's received a CMRP designation in 2005. He immigrated in 1982 directly to Sault Ste. Marie, Ontario, and currently resides in the Hamilton, Ontario, Canada region. He is semi-retired, and he now splits his time between process reliability and repair, developing and commercializing a new combined power generation technology, and as a marketing consultant. He is a lifetime member of AIST, having served specific roles on 3 separate committees, and is currently the co-chair establishing Decarbonization subcommittee under the Energy and Utilities Committee. Our second moderator is Felix Foschbach, who is beaming in today from Germany and has had a bit of a car trouble, so he may show up later in the presentation. But Felix has a BS and an MS and a PhD in metallurgy from the RWTH Aachen University in Aachen, Germany. From 2014 to 21, he was the R&D lab manager at AIST in Belgium. And since 2021, he's the product manager at Bosch Stahl in Kiel in southern Germany. Felix has also been part of the European chapter and vice chair of this AIST Decarbonization subcommittee. At this point, I'd like to turn the presentation over to David. who will introduce our first presenter.
Thank you, Charlie. And I'd like to give everybody a warm welcome on behalf of the Decarbonization subcommittee. We have 50 people now in the lead and the liaison network. We've been in existence for about 18 months, and with the support and guidance of the AIST staff, we've developed webinars, AIST tech conferences, and we're now planning for 2023. So if anybody is interested in joining us, please feel free to do so. You can get the details on the landing page of the Decarb subcommittee on the AIST website. Although we've done 5 or 6 webinars so far, this webinar series is developed jointly with the young professionals, and it aims to give introductory information about the overall situation with greenhouse gases, global warming, etc. As we all know, there are millions of people involved in the environmental movement, and within our industry, our leaders have already got a jump and developed pathways for their own companies using their own business models, and they are well advanced. So the purpose of this webinar series is to share some knowledge with all the people that are going to be affected in the industry, which is everybody. So what I'd like to do now is introduce our first presenter. Joe Morey is a chemical engineer from the Colorado School of Mines. He's been with US Steel since 1995 in a varied career, mainly in the primary end of integrated mills. He's now a senior consultant in process innovation, and he heads up the greenhouse task force for US Steel. For the AIST, he's the vice chair of Ironmaking, as well as being a valuable committee member on the Decarb subcommittee. Joe, I turn it over to you.
Great, thanks, David. Let me share. Okay, thanks a lot for that kind of introduction. I'm very honored to be able to present this sort of like a preliminary look, this 101 kind of look at this greenhouse gas considerations for what we've all been experiencing in the integrated plants throughout the world. In this webinar, actually it'll be 20 minutes, we're going to do a kind of a deep dive at the carbon footprint of, this is a fictitious, but if people look at the numbers, a realistic look at the iron making process from raw materials to the blast furnace. So I want the whole group out there, we're going to be one team for this. So if you can send some information in the chats, you're going to learn some items from this presentation, and I'm going to show you a new process. And when that process comes up, I would like you to share what you have just learned that applies to the new process. So to start this whole thing off, you have to ask yourself, why are we doing this? There's a lot of people who may believe or not believe in global warming and the impacts of greenhouse gases on that. But to be honest, all of our stakeholders are really pushing for this movement. And these are three of in the US, three of the largest consumers of steel that are out there. And you can read some of the things that they're saying. Whirlpool, they're decarbonizing their products and improving energy efficiency. Whirlpool makes a lot of appliances in the US. General Motors, obviously an automotive supplier in the US. hey, we're monitoring our suppliers and their environmental and social progress. So they're watching what we're doing. Caterpillar, they're looking at their first ever disclosure of the scope 3 greenhouse gas emissions data. So you ask yourself, what's the scope 3? It's interesting. So they're really looking at their own footprint. Before we get to that, just real quick, let's talk about the U.S. Footprint of this iron and steel. As you can see, in 1990, we were at 104,000 tons of steel production, I'm sorry, 104,000 million tons of CO2 from the steel production industry, and we're down to 37.7 million tons of CO2 equivalent. So this has been a dramatic reduction of CO2 that's been emitted by the steel industry. We've come a long way, but we still have a long way to go to get to this goal of net zero that many of us have. Now let's get into this scope 3 discussion here. So currently, in our accounting system for greenhouse gases, we measure what they call scope 1, which is all the carbon that comes in, or greenhouse gas emitting materials that come into the process, into a specific plant. And what they do is they subtract all the carbon that stays in the carbon form and leaves the plant. And that the difference is the scope 1 emissions of the specific plant. Now let's get into scope 2. Scope 2 goes a little bit up the food chain, where they look at, one of the biggest CO2 intensities on a given plant is electricity or power. So this is all the greenhouse gases that are associated with that. So that's kind of called out separately. But scope 3 is all of the other stuff, all of the other unintended or intended consequences of our business. Whether it be upstream, which you see that Caterpillar is looking upstream to see what was the greenhouse gas intensity of that, and downstream, what are the uses of our products and how are they helping in this overall carbon economy. So one of the things I like to say that if you just measured what you're doing in the plant, we could say that we can buy all of our steel from some other plant and bring it into your plant, process it, and then say that we have carbon-free steel. But that wouldn't really work, because all these indirect emissions that still travel along with that process. So here's the blast furnace process. I chose the blast furnace because the blast furnace, I have been working with the blast furnaces for 27 years. They have the largest carbon footprint in all of the processes throughout steel making. So I'm going to kind of go through that, and we're going to see some of the things that are related to this. So first, the first thing about the blast furnace, their fuel source, their major fuel source, of course, is this coke making. But it's not just coke making that's the problem. This all starts from coal mining to you're trucking the coal to the coal from the coal mine to the washing. So in this coal washing and preparation, there's a certain yield loss there of the coal that you get. So how much coal are you bringing and how much other stuff are you bringing in here? And then once you wash and prepare the coal, then you come to the coke plant itself, the batteries, and you have to dry the coal. You have to grind the coal, and then you charge the coal into the plant. And in a lot of processes, you recover the gas, and you recover the chemicals of there that have some carbon content in there. And then this coke goes and travels to the blast furnace itself. So I have all these little icons in here. You can choose here the way that you would like to transport the material from one process to the next. And in this presentation, which will be available to many on this call or on this in this webinar, you can see the factors that are here of the intensity of these individual modes of transport. The worst is, of course, is if you decided to fly the coal to the coke plant. That's a very high intensity of 3.37 pounds per ton of material per mile. And then, of course, the best mode of transport is the ocean or barge. And if you click on these links throughout the presentation, these lead you to some valuable resources that are available on the internet. Now let's go to natural gas. You know, the U.S., one of the things that's helped the U.S. decarbonize throughout the years is our abundance of natural gas that we have in this country that we're lucky to have. But, you know, even the natural gas industry has its own issues there. So, you know, we go through and we drill and extract the natural gas. And so gas liquids and gas separation have to happen at this point here because the gas doesn't come out of the ground as the same type of gas that actually comes into our plants. There's a lot of liquids and other types of you know, bad things in that gas. Then it has to go through a gas processing, a hugely energy intensive step where they're removing CO2, sulfur, nitrogen, and some other impurities in this gas before it can be sent to us at the plants. And now there's a gas transport step. So interesting thing I learned when I was putting this together, that there's a gas transport station every 50 to 60 miles in the gas transport network that's out there. And the reason why is just to take care of the frictional losses that happen throughout the pipeline. And so to repressurize it. So compression, that's a hugely energy intensive step that happens through the gas transport step. The next one is the natural gas gate station. So to transport the gas, they pressurize it to a large, to a high amount. So I have in here 200 to 1500 PSI. This natural gas gate station takes the pressure down from this transport network to the plant, or to what we call gas pressure regulation stations. So if it's coming to your house, for instance, it comes in at like a quarter pound for that. But if it's coming to an industrial site, it can come up to around 200 PSI. And the reason being that the plant has different needs throughout the plant of different pressures. So the plant will use a gas pressure regulation station to take the gas down to pressures that's required for the mill. But these are all, there's a lot of wasteful steps in here. I think you guys can identify, you know, there's this gas processing, transport, overpressurization, and also another overpressurization step to finally get it to the blast furnaces. So you have to ask yourself, what can we do better? Let's look at the pellets. Now, the pellets aren't really a fuel per se, you know, with a lot of greenhouse gas intensity, but you know, there's a lot of energy that goes into making the pellets. So, you know, depending, so you have a mining site. So how far is that mining site to your pelletization plant? It has to travel, and it goes through all these series of steps here, which applies these coefficients based off of what kind of mode of transportation you use. Then you go through the concentrating grinding mill. So what's the yield that comes out of this step here? How rich is your ore body, or how good are you at identifying good seams? and bring in just the right amount of stuff to the grinding mill. What kind of waste streams do you have coming out of here? Then it goes into the pelletization plant and ends up hardening the pellet to be a good type of pellet for the blast furnace. Okay, I'm looking at time here, so I'm going to just go through a few other items. So the interesting thing, electricity, the blast furnace is very relatively light on its electricity intensity. The only things it really has are you have to lift all this material to the top of the furnace, so there's a lot of work that's being done there. And there's some pumping that goes throughout the furnace, and you have to move the air into the stoves for this heating. So it's a very light intensity compared to the other types of energies there. And the one last one I'll talk about here is the hot metal and the slag. You go through this whole process, the heat and process these pellets, and you reduce the pellets using the carbon that you're burning, and you create a hot metal that's around 2,700 degrees that carries a lot of energy intensity there. Also, you create a slag with a tremendous amount of energy intensity. I'll go to the summary page here. So this last page here has a summary of all of these items. You can see it's in several different types of units, the amount of tons of CO2 that's responsible. So the biggest one here is the coke, followed by natural gas, and then limestone and electricity as far as direct measures there. So also we have, this recovery possibilities. You have coke, you can recover a certain amount of CO2 per year from that based off the amount of coke that you produce that actually goes into the blast furnace. So there's some fines that actually don't make it into the blast furnace as well. So this HBI and blast furnace scraps is an interesting one. It shows here, if you have a pre-reduced material, you can save energy in the blast furnace by using this material. But this has its own energy intensity because HBI, as you know, goes through its own process with its own energy intensity. And if it's a blast furnace scrap, that means it has to go through the process essentially twice, other than needing to be reduced the second time around. So it's actually really the most energy intensive thing that you can kind of use. So it's best to just not generate this if you can get away with it. But it's better than throwing it away. The one we didn't really talk about is this top gas, and this kind of if you look at the amount of energy here, or the tons of CO2 here, this the top gas here is 1.19. The coke is close to 2 million tons per year on this blast furnace, but you can recover around 860 MMBTUs of top gas per year from the blast furnace. So that's a tremendous amount of energy there. So there's many other there's many other processes that are here inside this presentation. If you guys can take a look and see some of those items there, but at the end of the session, take a look and see what things that are in that opportunities that you can point out from the blast furnace process can be used in this DRI process that we're actually replacing in many areas the blast furnace, because there's some commonalities that if we work on those two things together, that we can, can really make a difference to kill two birds with one stone. And so I will leave the group with that.
Thank you very much, Joe. As he mentions, this presentation will be available after the webinar for you to walk through yourselves slowly, share it with colleagues and discuss what's the impacts and what's the possibilities and all of the steps involved. I'd now like to move on to the second presentation. Javier Bonaplata is a mechanical, industrial and systems engineer with an MBA. He joined ArcelorMittal in 2004. He's worked in continuous improvement, purchasing, strategy and marketing development, and he's currently the CO2 strategy leader in the corporate strategy group for AM Global. So I'd like to turn it over to Javier to give us the second presentation.
Thank you for the opportunity to present. Again, I would like to take you through our approach to a steel emission standard. And the reason why I think we in ArcelorMittal, we have a unique perspective and quite a balanced approach is because when you look at our makeup as a company, we, I'm highlighting here a few of the highlights about us is that we're present in 16 countries producing iron and steel. And not only are we in Europe, the US, but we also are in many developing countries like Brazil, South Africa, Kazakhstan. So we have a very global perspective on decarbonizing the steel industry. And also we're not just blast furnace BOF producers, but we also produce significant amount of steel from DRI and scrap-based EAF. So we've, when we look at an emissions or a steel emission standard, we're really trying to find a solution that I think is quite representative to the challenge that the global steel industry has. Okay, so having said that, today I'd like to present two topics. First, take you through the rationale that we believe for differentiating primary and secondary sources of steel making, and why we think it's important when we set a steel emission standard that we make this distinction. And then I would like to take you through a high-level summary of how we would see a steel emission standards being developed. So on the first one, I am going to take you through some pretty obvious points, but I think it's important to build up the argumentation why ultimately we think we need this primary and secondary distinction. So the first point is we all know that to make steel, the main metallic that we need to make steel can either come from secondary sources, that's scrap-based from various sources of scrap, and it can come from primary sources, be it iron ore, right? One of them is finite, meaning this is scrap, the secondary sources. We're very much dependent on how much scrap becomes available when end-of-life equipment, buildings, infrastructure becomes available. And this is great. This gives steel a circularity credential that many other materials don't have. But this is definitely finite. What we do have is primary sources that are quite expandable to meet growing steel demand. So we keep this idea in mind as we go through the presentation. The next point is to understand where the CO2 challenge for steel is, right? When we look at the start again with secondary sources, scrap-based, when I'm producing steel using scrap, if I'm using clean electricity, actually the emissions are quite low. So producing steel from scrap sources is not only has great circularity credentials, but it's also the most straightforward way to decarbonize steel making. Of course, most of the emissions globally are coming from producing steel from primary sources. That is using iron ore. We today use gas and mostly coal to, first of all, extract that oxygen or remove the oxygen from the iron ore, from the oxidized iron. And we produce, as a result, we produce quite a lot of emissions for every, somewhere between 1-2 tons, depends on the technology. This is a rough numbers. And this is where the core of the emissions are for the steel making. So again, scrap is a finite resource, but also, primary is where most of the emissions for the steel industry are coming. So now, if we look at what's at a global level, what are we producing and how this is being produced? So here there's a graph on the global steel demand, or actually global steel production, and you can see that there has been significant growth over the past 30 years, right? We're talking about 2.5x growth in steel demand over the last 30 years. It's been driven by convergence of developing world to developed world standards. This is primarily driven by China in this case. And you can see that although the scrap portion of the steel being produced has been increasing, we rely mostly on primary sources to make the steel the world needs. Now, if we now fast forward for the next 30 years, right, we'll see that we'll have, in terms of global steel demand, we still have the developing world converging to developed world standards. That's going to increase the amount of steel demand in the world. We're also going to have, on top of that, we're having this transition to a clean energy economy, and that's going to require a lot of materials, including steel. And we believe that, okay, partially this will be neutralized by increased material efficiency, how we use materials. But in any case, in the most optimistic of the cases, we're still looking at 1.5 times steel demand growth. And when you look how this steel is going to be supplied, it's true that scrap is going to play an increasing role in making steel in the future, because there's going to be more scrap available. We just have to look at a rear view mirror, how much steel was produced in the past to have a good forecast, or how much scrap will become available in the future. But what's clear in this graph is that the world beyond 2050 is going to still rely heavily on primary steel making. So the challenge is we need to, if we want to decarbonize by 2050, you can clearly see here that we need to tackle decarbonization of primary, and we cannot rely on secondary end of life scrap solving the emissions issue that the steel industry has. Now, again, this is just one more argument. Right now, it's just this, it's quite intellectually interesting, but to understand why this is so fundamental in setting a steel emission standard is now when you look at the world, how the world is decarbonizing, right? We see that the decarbonization is moving at different speeds in different parts of the world. We have very advanced CO2 legislations in geographies like Europe, where there's an increasing cost of CO2 versus other regions. And at the same time, we can couple that to the fact that scrap is globally traded globally. And remember, scrap is the easiest way that we have as a steel maker, wherever you can substitute primary from secondary is the easiest way to decarbonize. So, you can clearly see that scrap is globally traded and easily flows to wherever market is offering the best value for that scrap. So if we put all these arguments together, we can come to the conclusion that first, scrap-based steel is the easiest way to decarbonize. I think we all agree on that. And primary steel actually requires significant investment and higher operating costs. We need as an industry to become carbon neutral by 2050. And in a context where primary steel will be significantly needed beyond 2050, we recognize that decarbonization is moving at different paces in the world. yet scrap is traded globally. So as you can see, we really need a standard that both rewards the increased use of scrap, because we have to stress the fact that scrap use should be incentivized as much as possible. The scrap is today already recovered at very high levels or a high percentages, but that still can be improved. But also we need a system that not only rewards the increased use of scrap, but also encourages investments in decarbonizing primary steel, because that's the only hope we have to meet the decarbonization targets as an industry, global industry, by 2050. So this is the rationale for differentiating primary and secondary. And now I'll go and dive into bring the high-level principles of what we think a steel emission standard should incorporate. Okay, so when we look at a steel emission standard, there's three key principles we think that should be this standard should meet. First of all, is that this steel emission standard should be a part of a dual score system. And what we mean by a dual score system is that we need a steel emission standards, but also this should be presented or published alongside a metric of your actual absolute emissions. So it's not a substitute to declaring what your absolute emissions throughout the value chain of your emissions of your steel is, but it's a complementary information. So that's a key principle we would like to put forward. The second one is that we're using clearly defined system boundaries. And now I know we talked many times about scope 1, scope 2, scope 3. What we believe in is the steel emission standard should really be irrespective of these scope 1, 2, or 3. It should be based on a fixed boundary, agreed boundary, and the key principles within this boundary is what we call it's a balance of a boundary that it's measurable, it's actionable, it's representative, and it's standardized. Okay, and the third point is which is key to the previous section I discussed why primary secondary is so important, is that the standard needs to distinguish between primary and secondary sources of metallic. Now, if we go on this dual score system, just simply to visually, this is just a hypothetical example, is that any standard, and this is for a product, it could be for a company or a facility, we are advocating for a steel emissions standard to show your progress, but that should also always be coupled to what is the total supply chain emissions that your again product, facility, or company has. So it should never be something used in isolation. Okay. Now when we talk about the boundaries, again, if you look at this diagram or graphic, here we're trying to replicate all the value chain steps to producing steel, and here we need to select a boundary, for a steel emission standard, and this is where we say it needs to be balanced around these four principles, something that's measurable, meaning that we don't have to reinvent anything to now comply with the standard, but it's part of the already ongoing measurement systems that steelmakers are making. It has to be actionable, meaning that it has to be what's included in this boundary needs to be elements that directly or indirectly we can have influence over in changing. It has to be representative, of course. It has to have enough. It needs to cover enough emissions throughout the value chain to cover, to be representative of decarbonizing this steel product or company, and it needs to be standardized, meaning that we need consistency in this boundary. So if we decide that, for example, iron agglomeration is included, this means that sintering and pelletizing is included. We can't just decide that our boundary will include, for example, sintering and not pelletizing. Okay, so based on these principles, again, I won't go into details. We can maybe in the Q&A there might be some questions, but from our point of view, this is where we think the boundaries should be fixed today. It could evolve over time, but we believe it should start at the core iron and steel making processes, and exclude the raw material extraction for now. It should also exclude ferroalloys production for now, to make more easily comparable decarbonization efforts between steel makers, and not so much influenced by what type of steels I'm producing. And finally, we actually believe that the boundary should include hot rolling. I think it's an important step to include. Okay, now when we look at the subject of this primary secondary that I discussed in the past, or sorry, in the first section of the presentation, we just to be transparent, there are different standards, right? And there's a standard, for example, or a family of standards that are looking at only absolute emissions. So I think it's worth to explain a little bit this little graphic here on the x-axis. We're seeing it's indicating for a steel producer how much, on one end, on the left-hand side, how much iron ore-based steel making or primary steel this producer is using, and on the other end, how much scrap, 100% scrap, a steel maker is producing. So basically, if I produce 100% based iron ore, I'll be in this vertical. If I produce 100% scrap, I'm on this vertical, and everywhere in between, if I'm a mix of primary secondary, I'll be somewhere in this horizontal. So with this standard, you can see that there is a threshold, whatever the threshold is set to be compliant or not compliant. And this is, you can see it's based on your absolute emissions. There's no consideration of where you are as a primary or secondary producer. And for this, let's say, approach, we do have some standards either developed or being developed. We have Klockner came up with a standard some months ago, and now recently we have the GSCC who has come with also a standard based on this concept. Now we have the other concept where this is where we are gravitating, which is this distinction between primary, secondary. So the same graph I described before, on your x-axis you have producers start on this side of the spectrum 100% iron ore based, and in this spectrum is 100% scrap based, and here's the spectrum in between. And the standard is actually based on a distinct primary target that a primary steel producer would have, and a secondary target that a scrap-based producer would have, in a sliding scale in between for producers who are somewhere in between, right? And this it's at the core of how we would address this need for a differentiated primary and secondary steel producing standard. And here, as you can see, a producer who's operating on this gray side or the right-hand side on this graphic, or this grayish side, he will be non-compliant if the threshold is set here, and producers inside the green would be compliant. So this is the core difference between the two standards. You can see that there is quite a lot of momentum in acceptance of this approach, which really addresses the needs of the steel industry. We have the SBTI, we have the German Steel Association, we have First Movers Coalition in the US, mostly driven, the IEA, Responsible Steel, Sustainable Steel Principles, the finance community, climate bonds, quite related to sustainable steel principles. And also we've come up with a concept also supporting this approach. Then how just to give you one more kind of level of detail, how we would operationalize this concept. The first thing we would do is we would first calculate, or this is what we have done, would calculate what should be the primary secondary target based on a global reference. For example, the IEA emissions profile or estimation, and we create this different target for secondary and primary, and a sliding scale in between. Again, because this principle, we need to focus on encouraging scrap use, optimizing scrap use. The standard, what we do is we would flatten the curve to incentivize the use of scrap throughout the entire spectrum, from primary to secondary, making incentivizing again the maximum use of scrap, but still we would leave a slope to reward the big investment steps that primary producers would make to decarbonize. And then what we would also propose to do is create categories inside of this a sliding scale to provide a transition roadmap to reward every decarbonization step that producers, both primary-based producers and secondary-based producers, or producers who are operating somewhere in the spectrum between primary and secondary. So they we have transition, let's say rewards, or some way to recognize transitions that they would have for decarbonization. I'm pretty much done. I leave the last slide just to give you, I've already kind of gave you a view on all the different standards and where they lie within, whether they're using a sliding scale approach or an absolute emissions approach on, and also just to highlight that all of them, they are looking at a fixed boundary approach. So defining a fixed boundary, and there are quite a lot of differences between them, but also at the same time, there's quite, I would say there's starting to be quite a bit of a convergence towards having a common standard for the steel industry. And apologies, I have not included here the GSCC. It just I just need to update this slide. So this would be an absolute emissions standard that is also being proposed. Okay, so I will stop there. Thank you for the opportunity, and look forward to the Q&A.
Thank you very much, Javier. We just have 5 minutes left for questions, so I'd like to select a few and ask the presenters to answer them as quickly as possible. We'll start with Joe. Joe, right now, each region of the world has some things that are specific, such as raw materials, fuels, and different processes. How does this affect each region's obligations now and going forward?
Yeah, so hey, thanks for the question, David. So as you can see, in the U.S., we'll just talk about the U.S. for a second. Everybody's got their own, sets of things that are available to them. Like we have natural gas, for instance, and relatively low cost electricity. So, this kind of helps us to be naturally carbon free. Each area is going to have their different challenges that they're going to have to look after, because we all have to balance this economic and greenhouse gas reduction at the end of the day to remain competitive.
Thank you. Javier, question for you has come up. Everyone is talking about the 2030 and 2050 deadlines. What do these dates mean for sharing a common measuring system?
Yes, thank you. Good question. I think we should definitely focus on 2030, because to have any kind of hope as an industry to be carbon neutral by 2050, meeting 2030 milestone is critical. And I think we we need this common measuring system. I think it's way overdue, because it's a key element that would facilitate investments that are needed now, so we can reach 2030 with already development of technologies, maturing mature decarbonization technologies, and already have significant progress in certain geographies in decarbonization. So I think having a common measuring system is critical at this stage, just to hit the 2030 ambition.
Thank you. Joe, we have a technical question, but it explores the use of hydrogen in our steel making as a replacement for carbon. If hydrogen were made available, how much hydrogen can be used as a reductant in the blast furnace? What is the practical limit and the challenges toward getting a maximum in practice?
So that is a very good question as far as the amount of hydrogen. As you know, hydrogen in the blast furnace has a kind of a quenching type of action that it does, because as it combusts, it turns to water, right? So then it has to filter up through the rest of the process. So there's a limited amount. So you can't replace all the injection with hydrogen. Almost to the point right now we're kind of leaning that we might as well just continue to use natural gas for the overall balance of the blast furnace in relationship. So I know in the DRI process they're looking at those processes to figure out how much can be used there. With our current construction and of these processes that we have now, but we're looking at other opportunities there.
Thank you. We have time for one, maybe two more questions. I'd like to throw it open to both Joe first and then Javier. Obviously, the steel industry doesn't operate on its own. What are the implications of how we coordinate and work with other industries in terms of the carbon emissions?
I'm glad you let me go first. This is a really awesome question for me. So this is one of the things, the opportunities that we all have to try to work together throughout industries and try to create an ecosystem that takes the whole processing, the whole manufacturing system lower and lower and lower. So for instance, what if we change all of our blast furnaces to DRI facilities? What happens to all that slag that offsets the carbon footprint of the cement industry, for instance? But there's other things that we could do. We have the plastics industry. They're putting plastics into the ground. What can we inject some of those plastics into our process and not put those into landfills? There's so many different types of things that we can do with our processes right now. And if we can look as a manufacturing community to see what kind of symbiotic relationships that we have, we could find that we'll uncover a ton of opportunities to really lower the overall carbon footprint without creating this huge albatross of economic upset.
Thank you. Javier?
Yeah, I think Joe hit the nail on the head, right? I think when we look at, it's very important, because I showed the steel emissions standard as an isolated kind of road for the steel industry, but we are so interconnected with other sectors, and we have such an influencing impact that we can have, as Joe's commented, on the cement industry. If the steel industry decides to go one direction or another, it could easily increase the challenge for the cement industry, or make it easier for the cement industry to decarbonize. If the steel industry, adopts a certain level of bioenergy, and that bioenergy, the off gases from that bioenergy production are turned into biochemicals for the plastics industry, suddenly we have decarbonized the key inputs for the plastic production for the plastics industry. So I think it's you know, for sure, as an industry, we need to focus on decarbonizing, but we need to keep in mind these interconnections that there's so much synergies in supporting or interconnecting sectors to decarbonize that needs to come into the equation of investment decisions that are made.
Thank you. We're now at 11 o'clock, so we'll have to bring it to a close. I would just like to, on behalf of the Decarbonization Subcommittee, thank the audience, thank the presenters, and thank AIST staff for enabling us to put this all together. And Charlie, if I could turn it over to you to close off, that would be good. Thank you.
Thank you, David. Confirm, David, that you're looking at the slide showing the Resource Center?
Yeah.
Very good. Everyone, if you will turn your attention to AIST.org, the Resource Center is where you will find a video recording of this webinar. And for members who have additional information that they seek, you can turn to what used to be called the Digital Library, but now is in one place, Resource Center at AIST.org. We want to also take a few minutes to show the upcoming live training that will occur in the second quarter of 2023. We have all of these conferences planned in cities, as you could see, from Texas to Florida to Indiana to Cleveland, Ohio, and finishing up in early June in Pittsburgh, Pennsylvania. So please stay tuned, take a look at AIST.org/calendar, and consider registering for any or all of these conferences. We'd like to thank you again for your attendance. And we look forward to seeing you again at future events. Just to remind you, if questions weren't answered that were put into the Q&A, they will be turned over to the presenters for direct contact. So we look forward to seeing you again, either in a webinar format or in one of our in-person conferences. Have a good day.